Hello everyone and welcome to the new part in Laplace Transform, which today you will go through how to find the inverse of Laplace Transform. So first we have this kind of f of t. We can get this Laplace Transform to be f of s. So the opposite right now, which will be the case when we need to return back to this one. So this is which is called inverse Laplace Transform. So there is no direct formula to get this inverse Laplace transform, but rather we will go through some few steps to think about this inverse transformation. So first we could imagine like the easiest way and the simplest as well. It's just get this from the table. So we have this table multiple times previously f of t, and we have the corresponding f of s. So instead of moving in this direction, we will have this f of s and return back to find what the corresponding f of t. So this is number one. Number two, also previously we were using this shifting property. If we multiplying this f of t by an exponential, this exponential with this f of t will do nothing but making this s to be shifted with this value of a. So right now we are doing the opposite. So if we have any shifting in s, this will be seen as there was an exponential, and then we can get this exponential out. But right now, previously was this exponential the last step in our transformation, the regular way from t to s. Now this one will be in the opposite direction, so this will be first to be done. And then if there is some shifting, we can go ahead and like reduce this one to the basic one without shifting and get this exponential outside to be simplified, and then we can get it from the table. Otherwise, if we have some denominator with a square, a cube, or any polynomial greater than 1, so we have two options. If this one can be factorized, so we will see if the denominator will be factorized. If yes, so it means we can use partial fraction. We'll through this shortly. If no, it means we can do completing the square. And then we can be again reduced to one of the first two steps. Otherwise, we can use the property in some smart way. So this need smart view. So let's keep this in mind, and then let's move forward, see how we can use these ones. So first, let's see, very simple example, find inverse Laplace transform of the following functions. First, we have very simple case. We have right now this f of s, and this f of s is equal to s plus 3 over s squared plus 10. Again, this is nothing, right? This in the table, but we have in the table something s squared plus a squared, and here it should be number, or it should be s. Both together, we don't know something like this, but rather we will do it in this way instead of having this numerator with 2s plus 3. So we can divide this numerator into two things, like we have this one and we have the other one. you just will do some partitioning of this numerator over the common denominator. So this one, it's nothing but 2s over s squared plus 10. Then this one is 3 over s squared plus 10. So from this way, again, this is something from the table. And again, this is something from the table. So just small modification. This part is actually a cosine. This part here, it's a sine, but it needs something. So we can add this a, which is root this number, and divide by this number. So we did nothing. So right now we can write down this f of t, which we can write it in this manner, like Laplace inverse of this function, like f of s. So this one will be 2, which is the same constant, s over s squared plus 10, which is cosine root this number and multiplied by t. The other part, which has this constant, so this is a constant, and we have root 10 in the denominator, and this one is a constant, so this one will be sine the same number, root 10 t. And then this is our function f of t. If we are moving the opposite way to get Laplace transform, we'll end up with this formula, the equation number 1. So again, we did nothing new, just we do this partition, and then we'll end up with 2s over s squared plus 10. The other one is 3 over s squared plus 10. One of them will be cosine, the other one will be sine. And just make sure that the sine will have some constant attached to this one. So let's do it here. What about if we have f of s, it's equal 4 over s squared plus 3 over s plus 1 over 3s minus 2. Again, we can see this as this one, it's in the table, this one also in the table, and this one very close to the table, but it needs small modification again in this formula. So we have 1 over s minus a, which coming from exponential. So this one is a previous table in the last 2 videos. So right now we can see this in the opposite thing. We need to get this 3 out. So to get this 3 out of the denominator, so we can rearrange the whole fractions. 4 over s squared is no problem. 3 over s is the same, no problem. And then 1 over third common. And here we'll end up s minus 2 over 3. So all terms together right now represent something from the table exactly. So right now f of t, which is the Laplace inverse of f s, will be equal to 1 over s squared, it's t, and 3 over s, it will be 3 multiplied 1 over 3, and 1/3, and this is the exponential e power 2 over 3t. And then this is our inverse Laplace transform. Let's see another example here. We have f plus equal 3s plus 1 over s minus 1 power 7. So here, don't worry about these powers. Again, let's remember something very quickly. If we have s power 7, and we can for sure get this power related to t power n, which is from the table exactly. If we can see this as minus a all to the power 7, it means we had this kind of shifting property. So it means we have e power 18 multiplied by the function. So moving on the other side, as we mentioned at the first slide, we need to get rid of this shifting from S, which getting this exponential out in t at the beginning. So here we need to get this out before doing any kind of simplification and see what kind of function in the table look like the other part of the function here. But take into consideration we have another shifting happen here in the numerator, so you need to make the same thing as s minus 1 in the denominator to be exactly the same shifting in the numerator. So we have to arrange this with one more step. So I will make this s minus 1 plus 1. So we did nothing here, and this is plus 1. And then s minus 1 power 7, it's still the same. For simplification, so again, we arrange this term 3s minus 1. So just like 3 here and here. And there is plus 3 and plus 1 over s minus 1 power 7. So again, we'll end up with this partitioning 3 over this one and all these constants over this one. So doing this partitioning, we will end up with this f of s will be equal 3 s minus 1 power 6, like one of these brackets will cancel out one of these 7 brackets, and then 4 over s minus 1 power 7. F of t will be the inverse of this one. Can think about it like in an easy way. So just you can cancel the shift here and here and return back this to the original form, which is e power 1t. And then you need to get Laplace inverse of the remaining part, which is 3 over s power 6 plus 4 over s power 7, which is here e power t is the same. 3 over s power 6, we have something previously here. We have t power n, Laplace transform was n factorial over s power n plus 1. So it means t will be to the power of the same power of s minus 1. So this one will be back here. So the same 3, 1 over s power 6, it will be t power 5, divided this 5 factorial, and this 4, it will be 4 t power 6, divided by 6 factorial. So this is how it should look like. And this is our Laplace inverse. So just no one get confused. So it means if we have t power n divided by n factorial, Laplace transform for this one will be 1 over s power n plus 1, which is the case here. If we have 1 over s power 6, it will be t power 5 divided by factorial, which is this term. And we have 1 over s power 7 will be 1 over s power 7. It means n equals 6, so it will be t power 6 divided 6 factorial. So hopefully this one is very clear right now. Let's see this example. So what happens if we have this f of s see something special here by s over s squared minus 3s minus 4. Right now, this denominator not sine or cosine. So we have s squared a number, and we have this 3s. So it means we need to see this one can be factorized or no. So this is the right question right now. So this can be factorized, yes. So this one, it's nothing but s minus 4, another bracket s plus 1. So again, so this fs can be rewritten as this 5s divided s minus 4, and we have s plus 1 here. So it means there is some constant over s minus 4 plus another constant s plus 1. So for these simple partial fractions, we can just substitute with s equal to 4, which is a term that makes this one equal to 0 from all parts but not this one. So I will substitute here 5s, it will be 5 times 4. And in the denominator, I will substitute here, so it would be 4 plus 1. Again, I'll do the same here. So for s equal s plus 1, I will substitute s equal minus 1, which is the term that makes this one equal to 0. And I will substitute with all terms in the original partial fraction formula here, but without substituting in the same bracket, which is s plus 1. So this one will be 5s, which is minus 1 right now. And then I'll substitute this one. So it will be minus 1 minus 4. So here this one is 20 divided 5. It will be 4. And this one minus 5 divided minus 5, it will be 1. So again, put this is a new form. So fs can be again rewritten as 4 over s minus 4 plus 1 over s plus 1. If you get it this way, so both of them are just simple exponential. So again, f of t will be nothing but 4e power 4t plus e power minus t. And then this is Laplace inverse of this one. So again, we have something here in the denominator, which is quadratic equation. And then this quadratic equation, we just examine this first to be factorized or not. So successfully it can be factorized, and we factorize this one, and then we ended up with this two simple partial fraction of equation of first order, first degree, and then we can get this numerators, and then fs will be ended with very simple fraction, like from the table, it's the transformation of the exponential, and then we'll end up with this simple exponential form. So let's see another example here. So what about if we have fs equals 3s plus 1 over s minus 1 divided s squared plus 1. It's a cubic equation in the denominator. So first, we need to get this partial fraction. It's already factorized. So this one will be equal something over s minus 1. And another thing here, which is s squared plus 1. The simple way, just you can get this constant by substituting s equal to 1 and get this numerator. So this one will be 3 plus 1 divided, I'll substitute with the other factorization in the denominator, so it will be 1 plus 1. This one can be get straightforward, so just I will assume I have as plus b, which is from partial fraction, the order minus 1 of the denominator. The order of them is minus 1. So here I need to get this a and b values. So again, I will equate both terms right now. So this is the old fraction, and the new one right now, this is 4 over 2. It will be here 2 over s minus 1 plus as plus b over s squared plus 1. Just take common denominator for this one again. L will be s minus 1, s squared plus 1, and right now we have, like, you can see it as cross multiplication. So we have here 2 s squared plus 1 plus as plus b multiplied s minus 1. So by equating coefficient, we can see here coefficient of s squared. So in this one here, we have this 2, and we have from the other side here, we have a. The opposite side, there is no s squared, so it will be 0. Then it means a equal minus 2. And for the coefficient of s power 0, we will have 2 and this part minus b, and the other side equal to 1, which means this b will be equal to 1. So again, rewriting this fraction, so f of s right now will be equal 2 over s minus 1. A and b right now are here, so just substitute 1 and 2, 1 and minus 2 in a and b. This one will be minus 2s plus 1 over s squared plus 1. Again, we'll end up with something, we already discussed this at the beginning. This one is denominator sine or cosine, but here we have to do this partitioning for the numerator. So again, we can arrange this in the new way, 2 over s minus 1 minus 2s over s squared plus 1 plus 1 over s squared plus 1. From these all fractions, it's all from table. So right now f of t, which is the Laplace inverse of this f of s, can be written down as 2e power t minus 2 cosine t plus sine t. And then this is the whole function in time domain, which has this Laplace transform written as the equation number 5. So again, let's recap this very quickly. We have this 3s plus 1 over a cubic equation, and this cubic equation, it's already here in this form factorized ready, and this s squared plus 1 can't be factorized further, so we will end up, we need to get this numerator for this first partial fraction, and the numerator, which is a first order, first degree polynomial for the second fraction. And then let's get the numerator, which is very easy for the first one, and just by equating the coefficient for a common denominator again, we will get this a and b. By getting a and b correctly, we have the final answer for this f of s in a simplified manner. This simplified fraction right now, it's nothing but very similar to what we have already mentioned in our table at the beginning. So this one is exponential. This s over s squared plus 1, it's nothing but cosine. The other part, it's nothing but sine. So this will be our final result for this one. Okay, let's move forward. So we have right now this f of s. and it's equal to s plus 3 divided by s squared plus 2s plus 5. And again, it's required to find this inverse of this function, so we need to find the inverse of Laplace transform. First of all, if we can consider this quadratic equation in the denominator, this can't be factorized. You can try, but again, it can't be factorized here. So it means we ended up with only one solution. We need to see if we can do this complete square or no. So let's remember together what this complete square looked like. So I will leave this numerator the same. And here this is s squared plus 2s plus 5. I'll take this s squared to be s plus half of the coefficient besides this s. So it's 1. So it will be s plus 1 squared. And then this will give us the first two terms, s squared plus 2s plus 1. So it means we have plus 1 and we have this 5. So it will be plus 4. So we have 1 from this side, and for the remaining part, both together, it will return back to this 5. What's the benefits of having this formula right now when we already end up here with s plus some constant squared plus constant, which is a denominator for sine and cosine from the table. So let's move forward on this one, and as we mentioned earlier, like we need to get the same shift in the whole term, both numerator and denominator, to be the same. And this is dominated by what's already exists in the denominator part. So I will make instead of 2s plus 3, I will make it 2s plus 1. And I will subtract the 2, which I already added here, and the remaining part, which is 3. So let's simplify this term. So it will be 2s plus 1, and minus 2 plus 3, it will be plus 1, over s plus 1 squared plus 4. Again, if we can do some smart partitioning, this part here, 2s plus 1 over s plus 1 squared plus 4, it's nothing but cosine. And the other part, which is this one here, over the same denominator, it's nothing but sine. So let's remove this shifting first, as we already discussed at the beginning. If we have shift, we can get rid of this shift at the beginning. So f of t, it will have this term e power minus t, which came through this s plus 1 term. And then we have to get this Laplace inverse of the new terms, which is 2s over s squared plus 4, and the other term, which is 1 over s squared plus 4. And this is much easier than before. Both, again, it's from the table. So let's put it down here, e power minus t. The first part will be 2 cosine the square root of this 4, which is 2t, plus sine 2t. But remember, we need to have 2 here, so I will just add 2 by 2, and I will have this half factor here. So, and this will represent our result for inverse of the Laplace transform of this given function. So let's recap this quickly. We have here 2s plus 3 over s squared plus 2s plus 5. Again, this denominator can't be factorized. We moved forward to get this denominator as a complete square. We did this in this smart way. We have s plus 1 all squared plus 4. And then we notice we have in the denominator the shift s plus 1. So it's required to get this to s plus 3 in the same shifting criteria. So I make it 2s plus 1 minus 2 plus 3, which is 2s plus 1. This is first bracket plus 1. And then we can do this partitioning again. We will end up with cosine and sine, but with the shifting already seen here, which is s plus 1. Remove the s plus 1 to return back to just s by taking this exponential out, which is e power minus t. And then we will have this simplified formula to get the Laplace inverse. Again, 2s over s squared plus 4. S over s squared plus 4, it's nothing but cosine 2 over and 1 over s squared plus 4. It needs 2 here in the numerator to be the inverse of the sine. And we add this half as a constant factor. And again, this will be the result as the inverse Laplace transform of the given function above. Okay, so let's keep going. We have the following example. We have this f of s is equal to s plus 5 divided by s squared plus 6s plus 34. So again, try to solving this one. Again, the 34 and 6 again can't be factorized. So the option right now is to do again a complete square or make it as a perfect square. So this s squared plus 6s plus 34, this one can be rewritten as, I'll keep the same numerator till the moment, and then this s plus 3 all squared, and then from this term we will get plus 9, and then there is a 34, so 34 minus this 9, we will end up with 25. So the same as we did before, we need to get this 2s plus 5 to have the same shift as the denominator, so I will make this as well to s plus 3, which means we add 6, so I will subtract the same 6 plus 5, and then the same denominator s plus 3 squared plus 25. So right now, just final rearrangement for this term, it will be 2s plus 3 over the same denominator, s plus 3 squared plus 25. And again, we have 6 and 5, these ones are minus 1. So it will be minus 1 over s plus 3 squared plus 25. And from this one, we know like this one is a cosine. And the other one, like this one is cosine and this one is sine. But we have this s plus 3 term, which related to the shifting due to the exponential e power minus 3t. So let's return back to this f of t. It will be e power minus 3t due to the existence of this plus 3 terms. So after removing these ones, we will end up with Laplace inverse of the new function, which is new 2s over s squared plus 25 minus 1 over s squared plus 25. And then both of them, they are already well known from the table. The first term is 2 cosines the square root of this 25, which is 5. So 2 cosine 5t. Minus the other term is, as we did previously as well, like this is the sine of the square root of this 25, so it's 5t, but we have to have this 5 in the numerator, so I will divide by this 5, and then this is the whole term right now, which is our f of t. So f of t right now, it's nothing but the exponential multiplied by a cosine and sine. And again, this is Laplace inverse of the given f of s. So again, quickly recap for what happened. We have this one right now, 2s plus 5 over s squared plus 6s over s squared plus 6s plus 34. And then we already figure out this one can't be factorized. So we'll try to do this by completing this square. We made this as s plus 3 squared plus 25. And this will give us the new term, which is here, 2s plus 3 minus 1 over s plus 3 squared plus 25.
the denominator is sine or cosine, depending on what kind of numerator exists here. So if we have s, this will be cosine. If we have just a constant, it will be sine. So we get rid of the shifting first, and we already got this exponential. And the other two terms, it's much easier from the table, one cosine and the other sine. And here we will end up with this formulas. So let's move forward and see another example also is using other properties. So what happen if we have this f of s equal, for example, like tan inverse 4 over s. So for sure there is nothing in the table or even from the previous properties using the shift or doing some kind of partial fraction or completing the square, something related to the tan inverse. But if we trying to recall something helpful, this tan inverse can be transferred into some fractional function just if we got the derivative. So let's remember together, if we have the derivative df by ds, previously this was like obtained using multiplying by t. So if I'm multiplying the function of t by t, it will give us the derivative on the s domain, and we have minus sign. So right now we are moving in the opposite way. So what this means? It means if we can get this df by ds, which is here, the derivative of this tan inverse, it will be 1 over 1 plus the term inside this tan inverse square, so it will be 4. So this one is 4 over s squared multiplied by the derivative of the term inside the tan inverse, which is minus 4 over s squared. For simplifying this thing, just I will multiply by s squared, all numerator and denominator terms. So it will end up with minus 4 over s squared plus 4 squared. This is df by ds. And if we are adding this minus sign here, this one will be positive 4 at the end. So what about returning back to the properties? So Laplace inverse of this minus df by ds, again, as we put outside, it's nothing but t multiplied by the original function f of t. So here, if we are getting this one Laplace inverse, this one will be t multiplied by f of t, and the right-hand side will be 4 over s squared plus 4 squared, which is sine 4t from the table. So what this means? It means if t f of t equals this sine 4t, it means f of t it's nothing but this sine divided by t. And here, this is our function f of t. If we are doing this Laplace transform, you will end up with this fs. And the opposite way, we got the Laplace inverse to be this one. So again, quickly to cover what happened here. We have the tan inverse. One of these functions we can deal with anything from the previous properties like linearity or doing this shifting or even use tricks of partial fraction or completing a square or even directly from the table. So one of the properties, which we already discussed previously in Laplace transform properties, it's the derivative in S domain, which was encountered due to this multiplication by t in the t domain. So what will happen? Just you will derive this f of s with respect to s, and then this function will be derived easily. And then after this derivative is done, we can claim that this derivative has Laplace inverse, which is the t multiplied by the function, which already unknown till now. And the other term on the right-hand side, it's something very similar to one of the function in the table, which is the sine. And then using this sine divided by t, we can obtain the final result, which is our f of t. So by doing this, let's see another example. You can apply also the same method. If we have f of s will be equal than s square minus 9 over s square plus 1. So again, if we have these functions, again, the easiest thing it will be the derivative. But just to remember something here regarding the len. If we are doing differentiation for this function, it will be much easier to do this len using the properties of the len or any logarithmic function. If we have a division inside this logarithmic function, it will be subtraction between two logarithmic functions. So this will give us more more comfortable way to derive the function. So right now I can just write down here this f of s. It's ln s square minus 9 minus ln s square plus 1. And then we can do the same thing. So just get the derivative. So the derivative here, it will be df by ds will be equal 1 over s square minus 9 multiplied by the derivative of this term, which is here, it's 2s, yes. And then we have here 1 over s squared plus 1, and here the derivative is 2s. So after getting this one, we can claim again, we can get this one as Laplace inverse for these functions, which this one should be t multiplied by f of t, but it should have some negative sign close to this df by ds, so I will put this negative sign here. Doesn't matter in which side you will put this minus sign. This 2s over s squared minus 9, it's nothing but one of the sine or cosine, the hyperbolic function. It's from the table. It's very close to the formulas of sine and cosine, but instead of having this plus sign, it's a minus sign. So this nothing but cosine, which is hyperbolic cosine, for 3t, and the other part is 2, which is cosine t. So f of t will be this 2 cosine 3t minus 2 cosine t, and then multiplied by minus t. And this is our Laplace inverse of this one. So again, this one is Laplace inverse of the given function. It means if we are doing Laplace transform for this cosine minus cosine over t, we'll end up with this ln function as we discussed here. So let's see another example here. So what happens if we have this f of s will be equal than s plus 3 divided s plus 7. And we have another term which is s plus 1 over s squared whole squared. So we can think about this in different ways. One of these functions, which is this ln, we need to use the derivative properties in S domain, as we already saw before. This one, it's just some simplification for this whole fraction, like you can do some partitioning or partial fraction. So it's let's assume it's just partial fraction. But we will use different methodologies. So what does this mean? This means we need to return back to the first and the very first property in Laplace transform. It's the linearity. What does this mean? If we have a function and this function, assume it's just f1 of s and this is f2 of s, and we have addition between both of them to give us this final f of s. So f of t, it will be nothing but the Laplace inverse of the first one plus Laplace inverse of the second one. So f1 of t, it's nothing but Laplace inverse of this f of s, f1 of s. How can we get this one? It's very easy, like we did before. If we have f1 of s equal ln s plus 3 divided by s plus 7, so we will make it again just 2 ln subtracted from each other, and I will do this derivative. So df1 by ds, it will be 1 over s plus 3 minus 1 over s plus 7. And then, just another color, we will get the tf1t, which is the Laplace inverse. I am taking this Laplace inverse right now, equal e power minus 3t minus e power minus 7t. So it means f1 of t will be e power minus 3t minus e power minus 7t over t. Sorry, there is missing minus sign here. So this is our first function. The other way, we don't need to get this fraction. And this fraction here, I don't need to get it using the derivative. So it's a very simple, like Laplace inverse problem. So let's see how this will be solved. So I have f2 of s equal s plus 1 over s squared all squared. So just do simple partitioning here. So it will be s over s squared, which is 1 over s, and we have another term, which 1 over s squared, and all these terms are squared. Just get this bracket squared. It will be 1 over s squared, and 2 over s cubed, and 1 over s power 4. It means you have this f2 of t. It's very simple from the table. The first term is t. Second term is 2t squared over 2 factorial. And the last term is t cubed over 3 factorial. So after getting this one here, again, we have right now f1 of t and f2 of t, which means we can end up this f total of t equal both of them, which is f1 plus f2, which is e power minus 3t minus e power minus 7t divided by minus t plus t plus t squared, which is 2 and 2 factorial will cancel each other, plus t cubed over 6. And then this is our f of t. Here. So again, something to consider here that's very important. If we have multiple functions added together in somehow, like it's a linear combination of multiple functions in S domain, and we need to get the inverse of whole function, we do need to do the same operation for all of them. So each one has its unique method to get this inverse done. So we can do this separately, and at the end, our whole Laplace inverse of the whole function, it will be the same, the linear combination of the same function with the same coefficient. What I mean, if we have some numbers here multiplied by this ln, and this plus sign it's minus, or another number multiplied by this other function, the same will happen at the end. Your f of t, it will be this f1 and f2 multiplied, added or subtracted with the same coefficient already exists in the original function above. So that's what I mean. You have to do each one with its, like, the corresponding easiest method to solve this problem. So let's see something else as well. So let's assume we have f of s will be equal to s over s squared plus 1 all squared. Some of these things we can solve this using partial fraction, one method, or someone can think about using this partial fraction, which will end up with we have something over s squared plus 1 and other thing s squared plus 1 all squared, which again you will return back to this term. How I can solve this term? So the partial fraction here is not useful. What else? There is nothing else. But regarding our properties, we had some property which is related to the integration. What's the benefit of this integration? We can see here, this 2s is nothing but the derivative of the function inside this square bracket. So it means if I can do some integral, the integral will be easy to be obtained. So let's think about it this way. We have a property, say, if we integrate this s from s to infinity in the s domain, this means our Laplace inverse of this one, to be more accurate, it's nothing but your previous function, you need to get it, f of t, divided by t. So it means if we have some function in S domain, this function can be integrated to give you another simpler form. So the inverse of the simpler form, it's nothing but the original function, which is still unknown, which needed to be and required to be obtained, divided by t. So after getting this one, just multiply by t, and then you will get your f of t. So let's apply this property here. So I will get Laplace inverse integration from s to infinity. I will put it here to u over u squared plus 1 squared du. It means this is Laplace inverse of this numerator to u, it's the derivative of this one. So the integration will be minus 1 over u squared plus 1. And the integration limits from s to infinity. So let's substitute with these ones. It will be Laplace inverse minus 1 over infinite, or limit as u tends to infinity, to be more accurate, minus 1 over s squared plus 1. So this one will be 0. This minus sign, both together, it will be Laplace inverse of 1 over s squared plus 1. So this is something we already know. Yes, we know this. It's nothing but your sine t from the table. And this one is still all these formulas we already defined here, just equal at the end f of t over t. So this means function f of t at the end, it's nothing but t multiplied sine t. So let's again recap this one here. We have 2s over s squared plus 1 all squared, which means this 2s here, it's the derivative of this s squared term, which means we can integrate this whole fraction to be another simple form. Why simple form? As we have this squared in the denominator, by integration this power will be less, which means it will give us something with power 1, which already something from the table, it's sine or cosine. So already we did the integration for this f of s with the limits from s to infinite. This is very important. This integration will give you this 1 over u squared plus 1 by substituting by the upper limit minus the lower limit. Then we'll end up with 1 over s squared plus 1. This one is just the sine t from the table at the beginning of our lectures. And then from the left-hand side, the Laplace inverse of the whole operation of this integration, it's nothing but f of t divided by t. So what's the value of just f of t? Just do this cross multiplication, which is f of t will be equal to t multiplied by this term, which is sine t. And by this one, we will come to the end of this Laplace inverse class and different methods to figure out how this f of t can be obtained back from many kind of f of s. We manipulating this again using something very directly from the table. We can use shifting properties to get rid of the shifting in S domain and get the exponential of t out. And also we discussed partial fraction or completing the square and some functions with like the ln or tan inverse or any kind of, or even some kind of complicated ln function. We can use the derivative, and we use the linearity if we have multiple terms together. Each one has its own method to get this f of t back. And finally, we saw this example with the integration property, which can, like, we can integrate with respect to s and get the function of t corresponding to the whole inverse of this Laplace transform. So thank you for listening, and see you in a new class and this new application for the Laplace transform.